Hi, everyone. So we're finally here. Chapter 4 on trigonometry. We're going to be working with trigonometric and inverse trigonometric functions later on. By the way, the functions of this chapter and the functions of chapter 3, the exponential and log functions, these are all non-algebraic functions. They're called transcendental functions. They're out there. Okay, but today we'll start very humbly. Section 4.1 on angles. And in particular, we're going to look at radian and degree measure. In fact, there are a couple of ways to do degree measure. So an angle can be thought of geometrically. You can think of an angle geometrically as a ray called the initial side being connected to another ray called the terminal side, and their common initial point is called the vertex. So geometrically, this is an angle. An angle is also a measure of rotation. You can think of an angle as being the rotation that's required to rotate this ray in such a way that's on top of this ray. So an angle is determined by rotating a ray, a half line, from an initial side to a terminal side, about this endpoint, this common endpoint called the vertex. A positive angle is determined by rotating the ray counterclockwise. A negative angle would correspond to this kind of rotation, a clockwise rotation. All right. Now, very often when you're working with trigonometry, we deal with standard angles. We try to place geometrically an angle in the xy plane, the Cartesian plane, in such a way that the vertex is at the origin and the initial side lies on the positive or non-negative x-axis. So let's say we have an angle where this initial side is then rotated to form this terminal side over here. It's a counterclockwise rotation, so it's an angle of positive measure, or it's a positive angle. If, on the other hand, you take this initial side and you rotate it clockwise to this terminal side, then you have a negative angle, or an angle of negative measure. Now, we often denote angle measures by either capital letters, also by Greek letters. Theta, phi, alpha, the first Greek letter, beta, the second Greek letter, and gamma, which is surprisingly the third Greek letter. We often use Greek letters to denote angle measures. By the way, at the end of this section, we're going to talk about coterminal angles. Those angles have the property that when you place them in such a way that their initial side is on the positive x-axis, so you have a standard angle has that property, then coterminal angles have the property that the terminal sides will also be the same, although you might have different types of rotation. It could be positive or negative, for example. Okay, so degree measure for angles. There are actually two ways of doing this. Decimal degrees, which are often denoted as DD, and DMS measure, degree minute second. We often associate angles with their rotational measures, right? The kind of rotation you're talking about. Now, in a full counterclockwise revolution, we call that doing a 360, right? That's 360 degrees. You go in a full revolution back to the initial side. The terminal side is coincident with the initial side. Now, this is something of a cultural artifact. The reason why it's 360 is that the ancient Babylonians loved operating on a base 60 number system. Many people say that this is related to the fact that there are about 360 days in the year. There's some controversy about that, but some people think it's related to the calendar. Okay, so we could use decimal degrees. So, for example, 35.6 degrees or 57.1 degrees. Or we could use DMS measure, degree minute second measure. You could think of 1 degree as like 1 hour, in the sense that there are 60 minutes in 1 hour, and then 60 seconds in 1 minute. So for example, this over here denotes 34 degrees, 30 minutes, and 20 seconds. Now in the homework, I do have you do some conversions, and I'll give you a basic idea here. All right, think of it this way. Think of this here as 34 degrees plus 30 minutes plus 20 seconds. And the idea is that you're going to convert the minutes and the seconds to degrees. How do you convert? You multiply by a version of 1. So for example, how do you convert minutes to degrees? All right, well, I want minutes in the bottom here so we get a cancellation, and I want degrees up on top. All right, well, we have 1 degree equaling how many minutes? Like an hour. 1 degree equals 60 minutes. And then it turns out that the minutes units here and the minutes units down here will cancel out. Goodbye. And then you're converting this into degrees. So you basically have 1/2 a degree, or 0.5. Do a similar process for seconds. Remember that 1 degree is equal to 60 squared, or 3,600 seconds. And it's a similar process. You add all these up. Likewise, to go from decimal degrees, let's say 57.8 degrees, let's say, what would you do? Here's the idea. This is equal to 57 degrees plus 0.8 degrees. Take the 0.8 degrees, convert it to minutes. Use a similar idea as what we did up here. Now, when you do that, you're going to get such and such many minutes. It's probably going to have a decimal part attached to it. You're going to take the decimal part attached to that and convert that part to seconds. So see if you can do this kind of problem on the homework. It's not in the primary notes. Okay. Now, degree measures are kind of unnatural in the sense that, well, let's say this is based on the calendar, right? Well, let's say you have smart Martians or smart aliens who love math. Maybe they'll travel over to Earth, and they're wondering, well, why do we care about 360? Why do we care that your stupid little planet goes around the sun in about 360 of your Earth days? Why should we care about your Earth days? I don't know. Maybe we're going to invade. But the 360, there's nothing, well, I mean, I'm sure it has a nice properties in some ways, but there's nothing special about 360 in this context. Radians, however, are special. Radian measures are critical, in part because in calculus, we assume you're dealing with radian measure. For example, you have to assume radian measure for x if you're going to say that the derivative of sine of x is cosine of x. That's only true if x is measured in radians, not degrees. But radians are just naturally just something that anyone, even an alien, might figure out. Okay? Radians are more mathematically natural. And again, they're typically assumed in calculus. And in fact, radian measure is assumed if there are no units present. So if you see a blank, you can just say, hey, let's pretend there are radians there. So what is a radian? What's its significance? 1 radian here is this counterclockwise rotation, this measure, where the intercepted arc length along this unit circle, this intercepted arc length, I'll write that out. I'll type that out. This intercepted arc length, from here to here, the piece that's cut off by this initial side and this terminal side. The length of this arc from here to here has the same length as the radius, the length of this guy from here to here, and the length of this guy from here to here. Notice this closely resembles an equilateral triangle. And what are the angles in an equilateral triangle? 60 degrees, 60 degrees, 60 degrees. So you might expect that 1 radian would be about 60 degrees. And in fact, it is. It's about 57.3 degrees. In fact, it's exactly this. For the following reason, let's talk about why. Okay, so we have 300, I'll type it out. We have 360 degrees in one complete counterclockwise revolution, right? Trying to move this. So in radians, what are we talking about here in radians? Well, in radians, we would then be talking about the entire circumference, the entire distance around this circle. What's the formula for the circumference of a circle of radius r? Well, let's start with 2 pi r. But wait a minute, the radius here is 1, so we just have 2 pi. 360 degrees equals 2 pi, and we can call these radians. I'll put it in brackets. Okay, now if 360 degrees is 2 pi radians, then that means that, over here, half as many degrees, 180 degrees, will be just pi radians, where I divide both sides of this by 2. 180 degrees is pi radians. What does 180 degrees look like? What does that rotation look like? Imagine this initial side. Here's the initial point over here. Initial point over here. All right. Half a revolution. It's a politician doing a flip-flop. You're going in the opposite direction now. That's 180 degrees. 180 degrees equals pi radians. Look at this thing over here, right? 180 degrees, you can bring this guy inside here. 180 degrees over pi radians, that's the assumed measure in here. That's going to be 1. So 180 degrees, okay, over pi. You don't have to worry about the idea of a quotient to a power idea here. That's not what's happening. If 180 degrees divided by pi is 100 over pi, all in degrees. Don't think of this as an exponent. All right. So this is 1, basically. This here is 1. 180 over pi in degrees, that's 1. It's 1 radian. 180 over pi is about 57.3. And that's we want 57.3 degrees. That equals 1 radian, roughly. All right. Again, 2 pi radians in a full counterclockwise revolution. More on conversion. Okay, converting between degrees and radians. Pi radians is equivalent to 180 degrees because 2 pi radians were equivalent to 360 degrees. So to convert 45 degrees into radians, what would you do? You have 45 degrees. You want to multiply by 1 creatively so that the degrees, the unit you want to kill out, is in the bottom, and radians, which is kind of like the unit you want to introduce, you're basically clearing out units. Radians is on top. Again, what represents 1? Pi radians over 180 degrees. That whole thing represents 1. 45 degrees times 1, all right? Basically, the degrees units cancel. 45 goes into 180 4 times. I should put a 1 there. Right? So when you multiply these together, you end up with pi over 4 radians. Hopefully, you'll remember that. You might remember, for example, that a right angle, 90 degrees, is pi over 2 radians. How do you go backwards? Let's say that you have 5 pi over 18 radians, and you want to convert that to degrees. So you want to multiply by 1 creatively. You put radians, right, the nothing unit, on the bottom. You want degrees on top. Pi radians equals 180 degrees. That's the flip-flop. Well, there's nothing really to cancel, right? The degrees basically carries over. The pi's here do cancel out. Pi divided by pi is 1. 18 goes into 180 degrees. 10 degrees times. We have 5 here. 5 times 10 degrees is 50 degrees. Another way of looking at this, you can think of it this way. Pi radians is 180 degrees. Pi radians is 180 degrees. 180 degrees divided by 18 is 10 degrees, and then times 5, you get 50 degrees. Okay. Remember, pi radians is 180 degrees. That's basically what I'm doing here. I'm breaking out the pi. Pi radians is 180 degrees. This might be a better visual for you. 18 goes into 180 degrees, 10 degrees times. Let's put a 1 there. 5 times 10 degrees is 50 degrees. All right. Now, one key observation. When you're calculating sine of something or cosine of something on your calculator, make sure you're in the right mode. Because sine of 50 degrees may be very, very different from sine of 50 radians. Make sure you're in the right mode. I'll put another color to emphasize that. If red's not good enough, let's make it a, well, it's already purple now. Let's add on some red, put some arrows here. Am I making the point strongly enough? Know what mode your calculator's in. If you're working out sine, cosine, and tangent. Otherwise, if you're doing like 2 times 3, then who cares? Okay, so next time we'll talk about the arc length formula.